Yeah. We thought it was metric.
It's not over here.
No. What? Why would you use a pencil? That's
But this is an erasing pen.
no. Does it erase well? Because some of those don't erase well.
Yeah, is it?
Uniform third.
Are we sure?
Maybe a mistake.
It is 13:30. I can't do this sometimes. Yeah, me too. 5th and 6th hour, I always take off my jacket. Skin gets hot, really. No, no, no. Why should we go? And then you divide it. Or I used to get cross multiplied.
How'd you do?
I got it. Killer.
We'd harp on stores a bit just to raise our confidence. Goodness.
Okay.
Oh,
Moving on. So differential equations should be a softie on the test tomorrow. If you're lucky enough to get one on the free response, it should be a 9, really. There's no excuse for it not being a 9. It's a gift. And that's not just me being crazy. I'm telling you, I don't know if we've talked about the structure of the AP test, but the AP test you'll take is a mixture of Calc 1 and Calc 2 material. So the AB kit sitting next to you, you'll have maybe 15 common, 20 common multiple choice questions and 3 common free response. You have 6 free response questions. 3 of those free response questions are AB, 3 of those questions are BC. The AB questions you should absolutely not just kill in 9, definite 9. Okay. I think I told you this, but I'll say it again. When you get your scores in July, you'll get a Calc 1 score and a Calc 2 score. And your colleges will get a Calc 1 score and a Calc 2 score, or A, B, and BC scores, sub-scores. It has happened. It's crazy, but it has happened that a kid got a 4 on AB and a 5 on BC. Mostly the second semester we think was more in Calc 2, but her Calc 1 got less. She didn't keep up with Calc 2. Okay? That said, though, on a question like this on the AP exam, the averages for an AB kid would be about 4. The average for BC kid who you're competing against would be 8 or 7. And you've got to kill it. Just got to kill it. Okay? So, that said, let's move on to today's lesson, which is not here. I did.
No, he was actually throwing a party.
It was a party.
Yeah.
Okay.
We had a party, so it was all worth it.
Yeah, math party. Okay. So, trapezoidal. When you hear the words Riemann sum, you think rectangles to estimate area under curve, yes? Okay, rectangles are good. Left hand, right hand are good. Midpoint is almost always better. And better than any rectangle is trapezoid. Okay, which we're doing today. And better than any trapezoid is Simpson's rule. We don't do, unless I can figure a way to get it in there. Simpson's rule is a way of estimating area under the curve that they definitely teach in most colleges, but it's not on the AP curriculum. So I would like you to at least be familiar with it. But today, trapezoids. Trapezoid is a superior estimation to area under the curve. The rectangles. Let's go, though, to the idea. The function 2 sine e to the x cannot be integrated. I think you know at this point that not everything has an antiderivative. Not everything can be integrated. Therefore, if you get a definite integral on something that doesn't have an antiderivative, the best you're going to do to estimate that integral is some kind of estimation method, like trapezoidal, all right? If I were to do this with trapezoids, I suppose I could graph it. Let's just draw a rough graph. I have no idea what this looks like, nor do I particularly care. Let's just draw something to look at, all right? So 12. If I want to do this with 4 trapezoids, just like rectangles, the first thing I do is subdivide it. If I'm doing this equally, then it would be 3, 6, 9, and 12, yes? You can see then, first and foremost, why trapezoids would be superior. They do a better job of following the curve. There's a little less error in it. We'll talk about error. That's actually the harder part of the lesson. In a second. But let's start here. For the first trapezoid, it would be something like base 1 plus base 2 times the height divided by 2, yeah? What's base 1? F at? No. First of all, bases in the trapezoid formula, they're not obviously what run horizontal. That's ridiculous. Bases in a trapezoid are what run parallel. They're the parallel. So in this case, the bases are not horizontal. They're vertical. So base 1 is F at?
F at 0.
F at 0. And base 2 is?
F at 3.
F at 3. And what is the height, which actually runs horizontal? The perpendicular distance between the bases? 3. Okay. The next trapezoid is base 1 plus base 2 times height divided by 2. What are the bases now?
3.
F at 3 plus F at 6 times the height 3 divided by 2. Third trapezoid, F at 6 and 9 added times 3 divided by 2. And the last, F at times 3 divided by 2. Now, working towards a little streamlined version, where it's very much a shortcut. Your work won't usually look like that. I just want you to see what kind of shorter form comes from. I think you'll agree that in every case, the height and the divided by 2 are common, so we can calculate that. If you look at what's inside now, at that point, because that 3 and 2 is gone, the parentheses don't really matter much. I could just say F at 0 plus F at 2 plus F at 2 plus sorry, that's a 3. I can't read my own writing. 3 plus F at 6 plus F at 6 plus F at 9 plus F at 9 plus F at 12. We? All right. Now, all that said, you wouldn't really show that typically in your work once you get good at these. Your first step when you get good at these is something like this. You'll notice that there are like terms on the insides, but not on the edges. So you'll often find, always find for equal subdivisions, that you'll have 2 of every interior x of I. 2 of every interior x. But only 1 on the outsides. Now that, if you think visually, makes a lot of sense. F at 3 is both part of the triangle, the trapezoid on the left, and the trapezoid on the right. So that F3 would happen twice is totally logical. Likewise, F at 6 is part of the trap on the left and the right, and the left and the right. So that those would all be 2, probably makes sense. Whereas the very first point and the very last point, they're only part of one trapezoid, so they only happen once, right? Right? Right. Okay. At that point then, that's typically your first step, typical first step. After that, you start picking up the old calculator. I would, on a function that's fairly ugly, I probably would name the function, put it in F1, so you could just call up F1 and the values in it. You with me? All right. Do you need to practice putting that in the calculator or that? All right. So then, if you have equal subdivisions you'll always be able to factor out the half of the formula and the height. Because they're equal subdivisions, they'll all have the same height. You then will start at the left edge and you'll have double of every interior point, however many there might be, and then a single on the edges. And that's what I said there. All right, any questions so far? Cool, all right. If you would then, estimate this please using trapezoids and 3 equal subdivisions. If you would like, I would start by saying let that be f of x. So that in your work, if you have f of x this and f of x that, somebody actually knows what you're talking about. If that looks probably pretty gross. Whatever. Somebody have an answer for this? So keep trying.
I think like 0.37, 367? Yeah. So, yep.
Yes?
0.367.
0.367?
529 over 1,000.
That? You guys come in denominator different. This is smart. It's going to get something. 529 over.
1,400.
Oh, shoot. 529 over 1,440.
I just
Yeah, it feels like. Did I get the common denominator wrong?
I felt bad just making you do it. So I think
I would have done it.
No.
Gotcha.
I gave you the.
Okay, try that multiple choice problem. Pretty common
I think
multiple
it's
choice.
like quick reset. Yeah. If you reset it.
You do not need to show work for that. Not sure why it's formatted so weird. So what do you say? It is E.
It's either D or E.
Okay, first thing I'd probably do is identify the height. Would you agree it's a region of 2 divided by 4, so it's a half. If you take out a half and you also have a half from the formula of the trapezoid itself, should have a 4th out front. Cool? Then double of the interiors. All right, we're good. Sounds good? All right, as is then often the case, unequal subdivisions. Depending on the problem, you might get unequal subdivisions. Now that could happen for a lot of different reasons. First of all, if you're collecting data, you might not collect it perfectly, all pretty princess at the same time intervals. If you're estimating the area under the square root of x, without a calculator, you probably wouldn't divide this region into perfect equal chunks like fives, because who knows the square root of 5? You'd probably divide it at places you could square root. So you'd probably do trapezoid from 0 to 1, and trapezoid from 1 to 4, and trapezoid from 1 to 9, and so on. You'd get unequal bases. So unequal bases happen for lots of reasons. Are you with me? Okay. In this case, then, if you have a table, if you have unequal subdivisions, then the idea of factoring out a height is out the window. And really, all you can factor out is the half, if you like. I don't even do that. I basically just do all the trapezoids separately. So the first, for example, from 1 to 12, you'd start off with the trapezoid from 1 to 3. So what's the height? 2. So you'd have a base times height, base 1 plus base 2 times height divided by 2, and I have a 2 out front for the height divided by 2. If this were free response, I would probably show F here and F there to make my work clear, but if it's multiple choice, I'd probably just go straight to the table. So what are the bases here? 4 and 10, okay? The next trapezoid then is a height of 2 again, and divided by 2, and this time the heights are, the bases rather, are 10 and 14, yeah? The next, though, what's the height? Height is 4 now, and the bases are 14 and 11. And then the last trapezoid, the height is 3, and the bases are 11 and 7, yeah? Okay, so I'm feeling something like 14 plus 24 plus 25 times 2 is 50, plus this is what, 18 divided by 2, so 9, so 27. And what, 38 plus 77, 24, 150.
Oh, I was right. I guessed.
You guessed?
Well, I guess that.
You're a master guesser.
I know.
All right, is that all for this slide? Yes.
100
Okay.
100% of the time.
Okay, now let's talk here. This is actually what makes trapezoids, this is one more reason why trapezoid's superior. So if I told you or asked you, hey, how many rectangles would you need to get the error in the estimation below a curve less than 1,000, you would really have to do it by trial and error. There's no way to know how many you would need. But for trapezoids, there's this idea of error bound. You actually know or can bound the error. And that makes trapezoids stinking wonderful because you can use them to get any desired degree of precision. I'll come to that in a second. But first, let's review rectangles. When you're using a Riemann sum, you can tell if it's an over or underestimate based on what two things go into your decision of rectangles over or underestimate. Okay, not concavity. Okay, actually, let's go here. Do you agree that both of these, one of these is concave down and one of these is concave up? Do you agree? Okay, and if I use right-hand rectangles here, do I get an over or underestimate? Over. And here, do I get an over or an underestimate? Over. So can we agree then that it's not about concavity, it's about slope or increasing versus decreasing? If it's increasing, what will be greater, the right side or the left side? The right side. And therefore, if it's increasing and you use right, you'll get an overestimate. But if it's increasing and you use left, the left side will be less than the right side, and you'll get an underestimate. So for rectangles, it's all about right hand versus left hand, and increasing versus decreasing. The concavity is not an issue for rectangles. Okay? So as an example, on the AP test, you might say something like this is an overestimate because I used right-hand rectangles on an increasing function. Is a pretty common error statement. There are 4 different error statements you can make with different combinations of right hand, left hand, and increase and decrease. You with me? Okay. Now, trapezoids. Consider trapezoids. Sketch a curve and look at a single trapezoid to estimate the area. Just one. What attribute affects if trapezoids over or underestimate? Let's talk increasing. Would you graph for me increasing concave up versus decreasing concave up? Right. Now, if I used trapezoids to estimate the area under these, just one trapezoid, let's say. If I used a trapezoid here, it would be the red. And would it over or underestimate? Over. Okay. Now let's use a trapezoid on a decreasing function. Would the trapezoid over or underestimate? Over. So we would say trapezoids overestimate whether it's increasing or decreasing. From that, I could gather that increasing or decreasing does not matter for trapezoids. What does matter is the concavity, okay? Concavity is what it's all about for trapezoids. So if on a certain region, on a whole region, F double is positive, that's supposed to be greater than 0, then trapezoids will what? Overestimate. Okay? And obviously, concave down, trapezoids will underestimate. All right, so it's all about concavity. Would you give that a go and then tell me the over-underestimate conclusion? This is, I know it feels like I could do that in your sleep, but it's pretty important and this is pretty common, so it's worth practice. It doesn't say equal subdivisions, but let's assume equal subdivisions, okay? Okay, that's probably what the work should look like. Is that what about what you have? Okay. I understand students are tempted and want to say because the curve is concave up. The response to that from my side would be, how do you know? How do you know? So why not say that? Okay, that's why it's concave up. Cite the symptom. Okay, or actually cite the cause, not the symptom, all right? So it's all the way back to the second derivative is positive. Concave up is nice, but you use the second derivative as evidence. Okay? Questions? Okay? All right. This is my favorite part. This is cool. So check this out. If you think about how much error could result out of using trapezoids, there are 3 factors that could combine to give you more or less errors. Think about that for a minute and talk through it with your math amigos. And I'm going to put my chili back in the kitchen. Not answering it.
It's like the concatenary, yes. Brady's out. How wide do these are? Yeah, how big the subdivisions are. Good night, Brady. Brady, you're a mood, dude. I'll see you tomorrow.
Can I see his calculator?
Yeah.
Plug in some, so you plug in some functions that are not difficult.
Destroyed the processor on your calculator. There's not a possibility. There's a way to try.
How are we doing?
Let's see how long it takes. Which means every 6 hours.
Okay. Give me one of the 3. How
Height.
height.
How concave it is.
How height. How high? So you're saying that if this curve looked exactly like this versus if it were up here, there would be more concavity here? You said how high? You mean how, oh, you mean the height along the x-axis? Is that what you mean?
I mean, that's like width. The width is one way. Like,
Somebody said height.
I said
Maybe
width.
the height
This-
is one of the trapezoids.
Okay, so this, the height of the trapezoids, would you agree that you'd get a heck of a lot of error if the scale here was 0.1 to 0.2 versus 1,000 to 2,000?
Integrating.
Wouldn't this error be just a huge number for a large magnitude region?
Infinitely small, then you
Okay,
get
so
lower.
the first thing is the width of the region. Think of it like how wide A to B is. The bigger the region, the bigger the numbers, the bigger the possible error. What else?
Like how
How concave, okay, so we don't go there a lot, but the degree of concavity matters. There are degrees to concavity. Imagine if I had the square root function, which is really slow growing. Is that trapezoid going to be off a lot or off very little? Very little. But if you look at a cube or something with a large second derivative, where the slopes are growing quickly, then you're talking a lot of error. So the degree of concavity. How much concavity? Now, I think you'll agree that if it's curving, it probably has lots of different second derivatives. So we'll probably not just focus on, what's concave at the starting point and ending point, but what's the greatest possible concavity? The last, what is that? How many subintervals? Yeah, if you do 1,000 trapezoids, then you'll minimize the error. So the number of subintervals.
Wait a second. Wait,
No, it's not.
Okay, no, I could talk the idea between 0.1 and 0.2, 1,000 versus 2,000. That has nothing to do with how many trapezoids. It's just how wide is the region. Now I could then say, how many trapezoids am I going to use in that region? That's different.
oh, so that's like the DX thing.
Yes.
So now A to B is not the DX thing.
No, it's the total region B minus A. All right. Now, that said, I'm not big on saying, here's the formula, go for it, but I proved this the first 2 years I taught this. It took about 40 minutes. It just didn't pay off. This is one of the few cases where I will say the error-bound formula is this, and I'll just expect you to know how to use it, but I won't be asking you to prove where it comes from, unfortunately, sadly. If you choose to look it up and go into it, it's really cool. You actually use ultraviolet voodoo twice, and use mean value theorem for integrals once. It's pretty great. It's pretty fun. But that said, I do want you to have a basic feel for why each component is in here. The error can be bound by, or I can know that the error is at a maximum due to these three factors. The error has to do with, first of all, how wide the region is. That B minus A, that's a measure of how wide the region is. Now, y the cube, that comes from the proof, sorry. The N, that also comes from how many intervals? Again, the 12, that comes through the proof. And the M. Now, the M is a measure of how concave it is. M really stands for the maximum possible concavity, or an upper bound on the concavity of the curve. You will often have to find, M is usually where you find the second derivative and find the upper bound of it.
What does that mean?
Okay? So it's the greatest possible concavity measure here. I'll talk about that in an example here, but let's go back one more thing and talk about direct versus inverse. The width of the region, does that relate directly to the error or inversely to the error? Is it the more region, the more error?
Yeah.
Okay, so that's a direct relationship. That's why it's in the numerator. M is concavity. The more concave, the more error, direct relationship. Or the more concave, the less error, inverse relationship.
Direct.
Direct, that's a direct relationship. And N, the more trapezoids, the less error, right? So that's an inverse relationship. That's why it's in the denominator. That at least, those make sense to me. All right? Let's talk about what a problem looks like. We're going to do an estimate, but then talk about the error bound. How good is your estimate? If I go to estimate this, first of all, 0 to 3 on this. If we use equal subdivisions, then what's the height? 1. And the divided by 2 is part of the formula. I'm going to let f of x equal x cubed. Okay? Then my interior, which is a collection of all the parallels of the trapezoids, what are they? F at 0 plus 2f at 1s plus 2f at 2s plus a single f at 3. Okay? 1/2, 0 plus 2 plus 2 times 8, so 16 plus 27. My estimate is 10, yeah? Do you agree?
45 halves.
Oh, that's not a 2, sorry, that's a 27, my bad. 43, 45 halves, yes, sorry. I read that last thing as a 2 bracket. That's not 2 bracket, that's 27. Sorry, 45 halves, do you agree?
I do agree.
Okay, cool. Now then, if I asked you, is this an over or an underestimate? How would you answer? It is an overestimate because the curve has a positive second derivative, right? On the interval. Are we cool? All right, now let's talk error band. The error in this, how good is this estimate of the true area? The error is less than or equal to. It's not the error is. If I knew what the error was, then I would know the exact, and I wouldn't have to do the error. Okay, you'll never know what the error is. It's an error bound. You say the error is less than this. B minus A. What is B minus A? 3 minus 0. Cubed over 12. What is N? 3 squared. Now M, you need to go off to the side and find. M is a max or an upper bound for the second derivative on the interval. Okay, so F prime is 3x squared. F double is 6x. What is the max of F double on 0 to 3? It is 18. That's it. That's the greatest possible concavity over that region. The most the slopes could be changing at any one point in that region is 18.
And so if it was like squared, would it just be a certain value then?
Yes. Okay, so we're looking at the error must be less than or equal to, let's see, I would be able to drop a couple threes. You might be thinking, is all this is such awesome preparation for Calc 2. That's why I hit this part, because this is just like Lagrange error bound once you see it. So all of this, know it's going somewhere, it's great stuff, but the error is less than or equal to, I get 9 halves.
So it's 9 halves.
Do you agree? Should I get arithmetic practice every day. Are you good?
I am.
Okay, so your error is less than or equal to 9 halves. 3 cubed over 12 3. Okay, I know my error must be less than or equal to 4.5. Now, if I combine a couple of these ideas, I know that that is an underestimate or an overestimate, did you say? Overestimate. So I really know that at the least, this could be 45 halves minus 9 halves. At the very least, the true area must be 36 halves or 18. Okay? It cannot be less than 18. Now, I could tighten that window and say it's even closer around the true area by expanding the number of trapezoids. Last case. How to say that I wasn't happy with an error of 4.5. I said, man, that's a really terrible estimate. Your boss comes to you and say, I need precision of this much. I need it within 1,000. How many trapezoids would you need? And then you'd use a program to execute that number of trapezoids. But how many trapezoids would you need to use to get the error to less than 1,000? Start with this idea. Error is less than or equal to B minus A. Is that going to change this time? Is B and A going to change for this problem?
No.
No, it's still 3 minus 0. N, is N going to change?
Yes.
Yeah, that's what we need to find. We want to find N. So that's going to stay N squared per the formula. The concavity measure, 18, that hasn't changed. It's still 18. Now we're solving for, actually we're not quite ready there. Now the next question, and this is a very common mistake, is where to put the 10 to the negative third or 1,000. Okay, let me tell you this. This is the most common error, and it is most definitely not here. All right, this is crazy. To anybody reading it, because you're saying basically you want the number of trapezoids to be less than, and you want to maximize the error, not minimize the error. You want error to be less than, or greater than 1,000. It does not go here. You want the error to be less than this, and if this is less than 1,000, then the error will also be less than 1,000. Okay, so error bound needs to be less than 1,000, and therefore the error. If you then focus on this side, now focus here, and solve. I could do a little bit of cleaning up. Can I multiply n squared over without fear of switching the inequality? Remember, when you multiply by a negative, you have to switch that inequality. But when you multiply by a positive, you don't switch that inequality. So can I move that n squared over without fear? You can. Why? It must be positive. Likewise, I can move the 1,000 over there. It's positive, so no worries. So I might get something like 27 times 18 times 1,000 over 12 on the left, and n squared on the right. And now let's do a little cleanup here. For example, 2 here and 3 there, and maybe 500 there. What's 27 times 3 times 500? 81 times 5, 40,000, 4,500? 4,050? No, that's not right. 81 times 5 is 410. 405 with 2 zeros. 405 with 2 zeros? You agree? Okay. N squared then, would you square root this, please, and give me the decimal? Square root of 400, what's that, 20-ish times 10-ish, 200-ish? 201.247. All right. Now, obviously, then, to answer the question completely, the question is, how many trapezoids do you use? You would obviously be a total idiot if you said, I use 201.247 trapezoids. That's stupid. N must be an integer. And do I round up, round down? How do I round? 201 would not be enough. I would have to always round up. Okay, you need at least 202 trapezoids. You always round up, no matter how close it is to the lower number, you always round up. Understood? You would have to do subdivision 202 trapezoids to get the error down to less than 1,000. You with me? All right. That should be enough to be able to do any trapezoid problem you see other than proving the trapezoid error bound. That's it. So, questions on 94? Oh yeah. Why wouldn't we have a test tomorrow?
It's Halloween.
I gave you a review.
Yeah, we were some.
Didn't I give you a review?
Are you learning Thursday?
Why wouldn't we?
Yeah,
Oh yeah. No, that's trapezoid extra
so
cut.
if we just
Why?
Brady,
Everybody?
No, we have a physics
Maybe
test
it's not Thursday versus Wednesday.
Why would you do that?
You're gone Thursday? Are all juniors gone Thursday or just?
No. I'm a special snowflake.
You almost got it.
Thursday again or Wednesday? Thursday again? Thursday? Guys decide. Thursday, no one says Thursday. Okay, blame it on Lily. Lily chose.
No.
Okay, test is Thursday.
Oh, come on.
What? I thought you really wanted
he's already changed it, loser.
I can't do anything this Halloween.
Oh, yeah.
It's Halloween. I'm
What is happening? You're welcome. The worst thing that could ever happen?
I'm
Like worse than the Holocaust.
Mr. Rickman.
But in this class.
Oh,
Really?
I'm at walking. I don't think at tomorrow and I get a study for physics the other today, and I'm like, I'm studying for
I feel like I want to have a test later.
oh. But it's true though, right?
Michael, you should show that faculty.
You saw the map problem? What's in the middle? There must be two in the middle. Yes, only by a two in the middle could the sums be all odd. Even. All right, extra credit for you.
Really?
Sure.
What is Brady extra credit for?
Solving that problem.